Is that okay? Sorry about it. So, okay. So now, as I said, when I was saying to two Gauss integration points, would allow me to have a four, let's say, coefficients. That means I can define cubic polynomial, and I am looking for two unknown values of abscissa, two unknown values of weights. So by the symmetry with respect to the interval, I can assume that these two weights are the same, W1, W2 to be the same W, and these abscissas to be symmetrically placed with respect to the center being psi equal to 0. So that means that minus psi1 is the same as psi2, and I call this psi. So if I want now to obtain what that is, I can write the cubic polynomial as such, C0 plus C1 psi plus C2 psi squared plus C3 psi to the power 3. I can integrate that. So this will give me 2 times C0. This will give me 2/3 of C2, and the others will drop. And I want to see how can I write this as the sum of all these products between weights and the values of the abscissa, given that these weights and abscissas could be simplified. Hence, I obtain this form that I want and the form that I integrated. And I simply compare these two terms. Obviously, if I find now the W weights are equal to 1, this will match. C0 here, C0 there would be fine because W will drop. And then from this last one to match 2 psi squared with the 2/3 C2, obviously I have to have a psi1 and psi2 to be equal 1 over square root of 3, or square root of 3 over 3. That means psi1 is minus 1 over square root of 3, and psi2 is plus 1 square root of 3. So this was really the kind of the other type of thing. Let me again go back to the sharing screen for this slide. So this was the case. Oops, now since it's killed the whole procedure, I have to do it again. Anyway, it doesn't matter. So this was the kind of stuff that I had to integrate. This was it. And then let's say this is the kind of thing that I was supposed to be integrating. So now I'm computing this at this value, and I'm computing this at that value. So this is psi1. And this here is psi2. And basically, what I do is basically I take the value of psi1, which is equal to minus 1 over square root of 3. And this is equal to plus 1 over square root of 3. And I simply take the function I'm integrating, evaluate for this, and I multiply product by 1. That means nothing really to do. Just take this value, sum them up, and this is the end of the story. So basically, what you can do is you can go back and complete the homework by using the numerical integration, and you can decide how many numerical integration you need to compute the stiffness matrices, and you can test really whether this what I told you is correct. For example, one thing I can just illustrate here: if you take a two-node truss-bar element, it should be enough to have a single Gauss point for numerical integration. If you take the same single Gauss point for the internal force and for the stiffness, you should get exact result. However, if you take a single Gauss point for a numerical integration of your loading, you should have a wrong result, especially if the loading is linear, unless it's constant, in which case this would be fine. But for this example, this was constant, so it should be fine. Now, if you go to a high order interpolation, a 3-node element, I'll let you know, I'll let you see yourself how many of these Gauss points you have to use in order to do that. So let me just, if you want to complete the homework, homework which is unfortunately erased, I can go back and basically that was question number D. You had A, B, C already defined. Let me put this text. Use Gauss numerical integration for cases 2 elements with 2 nodes, 1 element with 3 nodes. That's it. Okay. So this would allow you to complete the homework. That was remind again. I wanted to remind you again. That was like question of that was this bar where you had where you had here T bar, where you had this distributed loading B and stuff like that, and that was like that. And so this is exactly like using Gauss numerical integration I just explained to finish this problem. So that should allow you really to fully understand everything. Now, let me just wrap it up with a couple of things here. These are so-called continuum consistent interpolation. We have isospectral interpolation, so that means you can linearize and then discretize. We'll talk about that later. And isoparametric interpolation will allow you to do this. Now, recall by switching to isoparametric elements, what we have done, we have used element point of view. And this way we got advantage of being able to compute everything more fast in a way which is uniform, so the machine likes it, but we have lost the view of the global interpolation. So basically now, to go back to this global interpolation, you have to do this effort that actually would allow you to do that. And so the idea is really now we have to establish connection between the local and global point of view. This is done by so-called connectivity matrix, which is nothing but a Boolean matrix. That means it has only ones or zeros. It's very simple effect. One, when this local and global notation is the same, and zero if they are not. So let me illustrate that on a simple case where I have 5 nodes and 2 different possibilities. One, to have 4 elements, each one being 2 node elements. Or the second one, still these 5 nodes, but now I have 2 elements and each one has 3 nodes. So what would be these Boolean matrices? Simply for the first element, with the mesh consists of these 2 node elements, would be simply to say that W1 globally is the same as W1 locally. And W2 locally is the same as W2 globally. So that's why you have this first one, 1 and 1, which says that W1 or the first element is the same as W1 globally, and W2 of the first element is the same as W2 globally. Now, for the second element, this is no longer the case. Here you still have elements 1 and 2 locally, nodes 1 and 2 locally, but here are now called nodes 2 and 3 globally. So this second L will have shifted 1 and 1. That would simply mean that the W1 locally for element 2 is the same as W2 globally. And then W2 locally for element 2 would be the same as W3, and so on. The only thing is for the last element, element 4, basically this element is between nodes 4 and 5. But element 5, with node 5, we put the support. And so there's no place in the global set of arrays to put the virtual displacement. You remember that in global displacement, you only keep the virtual displacement if it's not at the node where you put the support. So here it stops at 4, this number of equations. And when you look at the element point, you have actually 5 nodes because it happens that the element 4 is between nodes 4 and 5. So what you do is simply you skip that one because basically there's no room, and this one has only one entry here. Now, if you have the same thing, that means 4 of these active nodes and the virtual displacement, but now the mesh is for 3 nodes. Your connectivity matrix is for the first element. 1, 2, and 3 locally is the same as 1, 2, and 3 globally. And for the second element, 1, 2, and 3 locally is shifted here. So there's place for 1 and 2. They are the same as 3 and 4, but there's no place for the last one. So what happens when is connectivity matrix is defined? Of course, then you can go to the virtual work and you say, okay, I have expressed my virtual work element-wise. That means element by element have these connections. Now I can express every of these element-wise connection in terms of connectivity matrix times the internal force and external force. So basically that becomes like a virtual displacement transpose. And here you have this global connection, which is LE transpose times FE. And the same thing for the external forces. So these LE are connectivity matrices multiplied by this, and this way you define the structure stiffness. So you can see structure internal force and structure external force. And same goes for the structure stiffness, so you need this 2 times for the both virtual displacement and of course incremental displacement. So basically this connectivity matrix allows you to place the results of the computation of the element level. So imagine the mesh with the 2 node elements. every internal force is a vector 2 by 1. Every stiffness matrix is a 2 by 2. The global stiffness is 4 by 4, and the global vector is 4 by 1. But so the size of these matrices is precisely that, it's 2 by 4. So when you start assembling, here you have 2 by 4 inverse, that is 4 by 2, times 2 by 1, you get precisely 4 by 1. And the stiffness matrix here is a 2 by 4, this is 2 by 2, and this is 4 by 2, so you get the final matrix 4 by 4. In other words, assembly is simply going in a systematic manner and taking the results of the element computation to put it in the global array, and this way you build your global array. And that is also done in the computer software. In fact, this was a doctoral thesis of Ed Wilson, one of my advisors. I had Ed Wilson and Bob Taylor as the PhD advisors. It was always fun to work with too. And this was really his software. It was his thesis. It looks today very easy, but it was done in 1965. So certainly it was not as easy as it is today. So basically, the real way how he did it, he was actually very clever in the sense that you actually condense, instead of bringing these L matrices which have lots of zeros and only 3 entries which are 1, or here that have only 2 entries which are 1, what he did is basically he defined a global L, which is simply for every element you condensed only the values of the global degrees of freedom that concern this element. So element 1 in 2-node mesh is basically 1 and 2, element 2 is 2 and 3, element 3 is 3 and 4, and last one is 4 and 0, because 5 doesn't have place in it. And here also for 3-node element, you have 1, 2, 3 for the first, and then 3, 4, 0 for the last. And then you go simply in this type of procedure, namely you take a component of your internal external force, component A, which is either 1 or 2 if it's 2-node element, or 1, 2, 3, which is 3-node element, and you take a particular element E, and you find the place in this table, and you place this result on top of this one. And this way you kind of add it up, and you kind of forget what was before. And the same goes for stiffness, only you need now 2 indices, A and B, and they go to this table for 2 different indices, always for the same element, and you simply achieve your assembly procedure this way. So that becomes really a very efficient way of constructing. So what we've done, we kind of divide and conquer. We did it for the isoparametric elements, and then we go with the finite element assembly. This is what is called finite element assembly, and you have this funny symbol that means this is summation plus let's say localization of where exactly this should go. So in conclusion, what I have to explain to you today is the following. I explained for 1D problem everything, the whole procedure of the finite element, let's say in 1 day. Hopefully you had it before. If you haven't, they say this is always good start. So basically I have a 1D example defining strong form, and then the weak form, and then Galerkin equation, and then this matrix equation. Once I've done that, at the end, if it's nonlinear, I also need the Newton method. I also explained the finite element technology type of thing, the role of the, let's say, different simplification in order to build this matrix equation that I have to solve. I can rely on the finite element assembly, which implies, summation of each and every element, and then localization of where they are. Then I can basically take into account the what you call it, the reference element, to provide this computation more fast. And I can use, of course, numerical integration. All these things will be clarified with the homework that I assigned you to eventually to look into that and hopefully work it out as we go along. So the same stages are exactly the same for the 3D problems. The only problem is the details are typically more elaborate because you have many more type of components to worry about. Typically you have a tensor notation and the choice of interpolation, finite element notation, and so on and so forth. So basically, some of these remarkable things is that we had very remarkable names who allowed us to have such a fantastic method. Certainly, the contribution of Gauss solving the set of large equation and the numerical integration was a big deal. And Irons, who had the idea about these isoparametric elements, numerical integration, and so on and so forth. Now, 1D models are very good because they allow me to illustrate very clearly, even with these rudimentary techniques with Zoom, everything I wanted to say. But of course, you cannot really illustrate how to solve all these problems for 3D case for other cases. So eventually, as we go along, I'll comment on that. So 1D problems are also not very demanding with respect to finite element approximation. Everything I said is probably the simplest type of approximation. more complicated cases you need when you have a 3D and 2D cases, because then it gets a little bit more tricky. So roughly, this is all for today. And tomorrow, I will only make a first lecture as we go along, and basically, so today that we have 3 sessions will be kind of made up with 1 session only tomorrow, 8:30, and then we will wrap it up before. Is that okay? Do you have any questions or comments on, or any other thing that we need to clarify? As I said, this, yeah.
Sorry, Professor, I have 2 questions.
Yes.
The first one is with the consistent linearization of the, where you have some kind of consistent model of finite element methods.
Yeah.
So if you implement this in commercial software like Abacus or something,
yeah.
how do you verify that it's correctly implemented? I mean, I remember you mentioned this quadratic conversions, but how do you control? How do you make sure that it converges quadratically in practice?
Well, typically, you know, this was a what I should say for this consistent linearization. The one that you rightfully mentioned is that when I said inconsistent linearization, that was something like something somewhere there, yeah. When I was explaining the incremental iterative method, I said that basically the property of the Newton's solution, consistent linearization, is the fact that you can show it in a simple case like here, that at every new iteration, the error is reduced quadratically with respect to the previous, because di is iterative solution and d bar is the true solution. And you can say that typically the error reduced quadratically. If here you have some value, here it's comparable to quadratic value of this value, provided that you have smoothness. The C is like a first derivative, second derivative of the function and stuff like that. So if you have smoothness, you can count on that. So how do you observe this? Basically, when you come close enough, when you come to value which is close to 0, every new iteration is doubling number of zeros. That's what it means, because the difference in error is basically this di minus d exact, and every new iteration is making it quadratic. So if you have a 10 to the minus 2, then it becomes whatever, 10 to the minus 4, 10 to the minus 8, and so on and so forth. So basically, this is the kind of ideal case when the function is smooth. And again, this has to be smooth enough. So now, in some cases, you don't get this, and especially you don't get it everywhere. But the idea is really, and the only thing I can try to show is some of the computation from very different models that you use, from large geometrically exact beams to plasticity and stuff like that, you know. So in the commercial software, unfortunately, this had not been implemented. Especially we have a software in France, which is free, which you don't pay any money for, because it was developed by nuclear industry, which was always very rich. So these are software that are called Code Aster. This is developed by Electricité de France, or Custom, or now it's called Cust3M by this nuclear institute, COA. For this software, if I remember correctly, since they didn't have the same skills of computing, and first they work on many much more complicated models, plasticity, damage, and all that stuff. They didn't have the same skill in mathematics like people who did this in other places. So they never really provided a consistent tangent module. So here the convergence is kind of linear or quasi-linear. It doesn't really increase the number of zeros in the residual so quickly. So it took forever to get something to very small values. So what they decided, they said, okay, you stop iterating when the residual is only 1% of the initial residual. But the initial residual, if the increments are big, could be very big. So it was very scary. I was always, when we started working in Electricité de France, this is one of the first things that I told them, of course, for funding that they gave us in return, is that basically the iterating to very small values is very important. Because if you're working with plasticity and damage and you're not iterating close to 0, you're accepting kind of mistakes which are really not normal. And because the plasticity and damage are path-dependent procedure, so if you're not iterating, that means you're not solving the exact solution. You're actually solving a little bit on the side. But you know, for plasticity, this could be very dangerous, because you know, plasticity is this. If you think of a plasticity as a phenomena, let's say this is supposed to be your this is supposed to be your response. You know, you're supposed to have something like that. But if you're not iterating correctly, you might be, you know, you accept an error here, then you accept error there, then you accept error there, then you accept error here, then you accept error here. So I'm exaggerating on purpose, because in every of these increments you accepted certain error. So here, if you unload, you know, when you unload from here, this is your plastic deformation. When you unload from here, this is your plastic. So see, it looks better, but it could have looked worse, you know, basically, because here you get even more plastic deformation. It all depends what you want. So I'm saying basically, you know, in all these situations, it's very important to be able to converge down to a residual which is small enough. So the problem is many commercial software, they're kind of hiding what kind of method they're using, and they often now have these automatic solvers and stuff like that. So if you expect in nonlinear problems just to press the button and go to the solution, most of the time it's probably not true. So you should be really kind of warned that this has to be a little bit taken with the precaution. And then
my question regarding this commercial software is because I run the program, I see everything looks nice and you know, as it should, but I don't actually know if it's convergent quadratic. I cannot say yes or no.
Yeah, the only thing you can know is by taking a validation example, basically, where you know what results should be taken. We'll talk about it when we talk about 2D, 3D. There's one thing like called patch test and stuff like that. Before starting to use the most complicated formulation, one has to start by using a simple enough formulation and really validating that this works. So that means in terms of interpolation, finite element, it means you solve patch test. In other words, ability of the element to represent the constant stress field or linear stress field, something exactly. So if you can solve this problem, there's still guaranteed that in the convergence you'll achieve, if you start decreasing element size more and more, that you will have a constant stress more or less represented. In the Newton methods, the same thing. You try to solve something, we have only 1 degree of freedom. Of course, this is not useful solution because the structure is not well modeled, but maybe with 1 degree of freedom, you can work out some kind of numerical solution or analytical solution on the side. And you can see that the software is doing fine in terms of the convergence rate. Of course, when you have a very fine mesh and you have thousands of equations, then it becomes more tricky. And then you can also go to local minima and stuff like that. So I have it in a book. I didn't really discuss here too much, but there's something called line search. There's something called optimization methods to get more robustness. There's something called arc length method, and lots of, I mean, solving a nonlinear problem with the commercial software is always a trick. One should at least be sure to know what kind of element you can use. I mean, I even when we worked for Electricité de France and this COI and this Institute of Radio Protection, either I was able to impose my own codes, or if they had their own codes like custom or what you call code aster, these are open sources, so you can immediately see what exactly who did it and how they did it and so on and so forth. And then you know what is the potential weakness of this problem. Otherwise, if you just trust that this is element number, this and that, like I was once in this what do you call it, a benchmark competition organized by OCDE under, let's say, initiative of this Institut de Radio Protection Nucléaire, because they wanted to study what happened with the penetration of this reinforced concrete slab with the projectiles. You know, like it was the part of the study of this, what happens when the big planes would crash. So you can also study what happens when the explosives will crash. And we had crazy results for all different software, from Dyna 3D to Abacus explicit to all kind of stuff. And I said, your results are so much in dispersion that you should first start by material testing to know what exactly structure is doing in terms of quality of concrete and terms of quality of steel. And then you go to the global discussion. So basically, it is very much open solution. I just said, you try with the simple problems to gain confidence in your software tools and the elements you're using. It does not mean that for the most complicated problem, you're 100% sure that it delivers a perfect result. But luckily, that is why they need you. if they had the program, these guys who have money to develop these programs, if they had the program that press the button and then simply does it, they would kick out most of the engineers because they have too good salaries for something that could be done by something very cheap. So luckily, that's that's something I can say. There's certain thing in terms of experience of the class of problem you do and stuff like that. That's why I guess people stick with the same line of work and companies and stuff like that. The problem is, for example, in nuclear industry, I worked there for 15 years with people there, and I get to know almost all the big names in France who are working on that. But nowadays, you have this energy transition in France, where the government is giving lots of money and pushing people to switch to renewable, like wind turbines. So Commercial d'Énergie Atomique, CEA, has changed the name. They became CEA squared. That means Commercial d'Énergie Atomique, Energy Alternative, meaning that these guys will start making wind turbines. But believe me, between nuclear industry and wind turbine, there's a big difference. So most of those engineers who had big experience with nuclear industry, I don't know how they adapt to wind turbines. You have to be a professor to adapt to this better. That's the idea. So I don't know if I helped with my answers, but this is wisdom I can offer. Is that okay?
Thank you very much. You gave me some food for thought.
Okay. Any other questions or comments? Okay, fine. So I took you a little bit, 10 minutes or so more. So tomorrow we may be short in 10 minutes, not to burden you. So we start 8:30. We do only one session. Okay, guys. See you tomorrow. And thanks for hanging in. It's probably not as easy listening, but at least you are sitting comfortably. Okay. Bye-bye, guys.
Thank you very much.
Sure. Bye-bye.
Thank you.
Bye-bye. Thank you.
Bye-bye.
Bye-bye.
Thank you.
Thank you, sir.
Sure.